to us today from UC Berkeley, where she is. I want to make sure I get the name of it. Yeah. What is it? It's a big deal. Yeah, no. It's a big deal. But the question is, it's called a Chancellor's Postdoc. Anyhow, Rayna was an undergrad at Berkeley in the Department of Integrated Biology at UC, using vertebrate zoology. Then went to get her PhD at Cornell, where she worked with Kelly Studio, doing a kind of variety of really interesting projects. She's kind of focused on a couple of different things. A lot of work in Central Africa on amphibian sort of biodiversity, including some disease work, speciation work, which I think she'll be talking to us about today. Always with sort of an eye towards working on sort of relatively unknown, really interesting groups of tropical neurons, and also applying that work at least at some level to conservation issues. She's also working in Brazil on amphibians. In Brazil, she's got a project that's just coming out right now on hypercentimeters in the eastern U.S. She's working on a variety of different kinds of projects, but again, always with an eye towards patterns of diversification and at least to a certain extent conservation issues. She finished up at Cornell, and in August, I think, this past August, moved back to Berkeley to get this, as Tom and I were saying, very fancy and really, very, very impressive Chancellor's Fellow postdoc. And that postdoc, should you not be aware of it, especially for those of you thinking about postdocs, is one that what comes with that, there's such a sort of strong endorsement of the candidate that if a holder of one of those postdocs gets a position in UC, the Office of the President pays the first 5 years of their salary. So it's a very impressive honor to receive one. Before I turn the stage over to Rayna, I just wanted to say that she's leaving tonight, and we were thinking about different ways that we might have a dinner. And so what we're going to do, she leaves early, and so what we're planning on doing is at 4:30 this afternoon, 4:30 today, on the roof of the Botany building. You don't know how to get to the roof of the Botany building. You go in the front door, you go up the stairs, you can't go any further next to And what we'll have is at 4:30 today on the roof of the Botany building, we will have P, that's pizza, and B, that's beer. And so if you like pizza and beer, swing on by, have a slice, or have whatever you want. Hang out, visit with Rayna, for an hour or two before she has to scoot back up to LAX. And then the third thing is it's P and B and T, and T is turtles, because that's where we have 30 western pond turtles from Lake Elizabeth that you might have seen that are paddling around up in cans on the roof of the pond buildings. So we all hang out and play with turtles and pizza and beer. And that doesn't sound like a good thing.
either adjacent islands or the continent of a population that then diverges to form a new endemic species. Or you can also have in situ diversification of resident island endemics. And the relative contribution of these two main modes in generating endemic diversity on islands correlates with a number of characteristics that are unique to an archipelago. And so the importance of in situ diversification increases with island age, size, and remoteness, whereas dispersal dominates in really remote archipelagos, archipelagos that are near continental sources that are composed of many small islands, where in situ diversification is less likely to proceed. And there are hundreds and hundreds of studies, of course, that look at the contributions of these two mechanisms in generating endemic species on islands. But they tend to focus on really young and remote archipelagos, so like the Hawaiian archipelago or the Galapagos. And a lot of the focal species tend to be organisms with high dispersal ability across saltwater barriers, so things like birds. And of course, the ones that have garnered the most attention are the ones that have radiated extensively within islands, so like the knoll. And the system that I'm going to talk about today is really different from some of these more classic systems, in that the islands are orders of magnitude older. They're pretty close to the continent, and they also host a lot of endemic species from groups that we tend to not find on oceanic islands, so organisms that we think of as being poor dispersers across saltwater barriers. So the Gulf of Guinea archipelago is located a few hundred kilometers off the coast of Cameroon. So here's a little inset to show you where we're looking. And they remain isolated, or 3 of the islands in the archipelago are volcanic, and so they've remained isolated from the continent throughout their evolutionary history. But because they're relatively old, they've accumulated hundreds of endemic species over this time period. And so there are really, really high levels of endemism, much of which we're still working to just describe. But across all taxonomic groups, really, really impressive levels of endemism. And a lot of this endemism is really taxonomically disparate. And so that indicates that this endemism has been generated predominantly by dispersal from the continent as opposed to in situ diversification, or at least it appears to be the case. And we also do find some instances of sister species that are distributed among different islands in the archipelago. And so that indicates that dispersal between islands in the archipelago has also been an important source of new species endemism. So, as I mentioned, this island system is pretty special in that it hosts a lot of poor dispersing species. So it has a number of endemic amphibians, also shrews, which is pretty incredible, and some fossorial reptiles. And I'm going to focus on the amphibians. So there are 7 endemic species, including a Sicilian, which is a fossorial amphibian, and 6 species of frogs, and they're all from a bunch of different families, so really, really taxonomically diverse. And the prevailing hypothesis for how frogs and Sicilian and all these other poor dispersing organisms would have colonized the island is assisted dispersal on large vegetation rafts that are swept down major river drainages into the Gulf following a rain event. And there are 3 major rivers that dump into the Gulf that could potentially serve as a source for these types of vegetation rafts. So there's the Niger River, which originates way out up in West Africa. The Congo River, which is much larger than this, and it originates all the way out in East Africa, out here. And then the Ogooué River, which is a major river in West Central Africa. And so even though, in looking at this map, the Ogooué River is clearly the closest to the islands, the freshwater currents in the Gulf direct the freshwater coming out from the mouth of the Congo and the Niger rivers towards the islands. And so a vegetation raft originating all the way out in West Africa or even all the way out in East Africa could feasibly reach the islands. It would just have to travel a long way to get there. And so we can try to reconstruct the colonization history of the island's endemic amphibians by taking a phylogenetic approach. So sampling putative ancestral species or sister species on the continent and looking for the ones that are most closely related to the islands, and then looking at their distributions and trying to figure out which of these river drainages is likely to be in force. And so people have done that for most of the amphibians on the islands. And they consistently find a pattern of the closest sister taxa on the mainland being an East African species. Which seems crazy because they would have to go really, really far down the river to get there, but it could be possible. However, these studies all suffer from relatively poor taxonomic sampling, not because people haven't tried, but because it's pretty hard to work in some of these places. And so our interpretation of this pattern is of course biased by the sampling that's available, and it means that we still really don't understand the evolutionary history of this really enigmatic fauna and how many dispersal events there were they all coming from the same places. Basically still have no idea. So I wanted to address this question, and I chose to focus on the island's endemic reed frogs. And that's because they allowed me to address a bunch of questions simultaneously. So they're thought to be one of the only lineages of vertebrates that diversified within an island in the archipelago and also dispersed between islands in the archipelago. So we have the Sao Tome giant reed frog, which, in case you haven't seen reed frogs before, most species are about this big. And so the giant reed frog is about this big, but it's pretty big for a reed frog. It's the biggest one in the genus. And it's only found above 1,000 meters elevation on Sao Tome. And then its sister taxon is, doesn't have a common name, but we'll just call it the Sao Tome Principe reed frog. It's found from about sea level up to 1,400 meters on Sao Tome. And so there's an area of sympatry with the large species. And then it's also found on Principe, where it occurs up to the summit, which is about 1,000 meters elevation. And so this mini little radiation of frogs lets us look at a number of questions, including potential colonization routes from the continent, the sort of mechanism of in situ diversification within Sao Tome, if it did in fact happen in situ, and then dispersal between islands in the archipelago. And so those were the three main things that I chose to address in the system, and I took a multi-locus phylogeography approach to reconstruct the evolutionary history of the mainland sister taxon and figure out which species that was, and then I used a genome-wide SNP approach to look at more specific patterns of divergence within the island system. So first we'll look at colonization routes from the mainland. So lucky for me, a recent study identified a good candidate sister taxon on the continent because this genus has over 130 species in it, so it would have been a complete fishing expedition probably if I hadn't had this starting point. And that sister taxon is Heterolius cinnamomeo-ventris. I'll try not to say that too many times today, but the common name is cinnamon belly reed frog, so it's not much better. So this species is distributed throughout Central Africa, and so that distribution a priori rules out the Niger River as a potential colonization route, but either the Congo River or the Ogooué River could potentially serve as a dispersal route to the islands. And so I took a range-wide sampling of this species complex, it turns out, and found a lot of divergence, luckily, in this group. And you can see here, so we have, this is the sampling throughout Central Africa, and then here are the island species shown in pink. And this is the mitochondrial phylogeny, or phylogeography, that shows that these green populations of Cinnamomea-ventris are more closely related to the island endemics than these eastern, sort of north orange populations. And so this pattern suggests that a population from West Central Africa, or maybe one of these western drainages of the Congo, is a likely source population for this dispersal event, and that it's very unlikely that a population all the way out here in East Central Africa is the source population. And then this is just a species tree analysis of multiple nuclear that finds the same relationship. And it might not seem like a major surprise because this river is much closer to here, but ours was the first study to find this pattern, and I think it just goes to show that trying to understand all this cryptic genetic diversity in these really widespread mainland species is going to be a really important part of understanding the evolutionary history of these island faunas. So we have a lot more work to do in terms of filling in these sampling gaps on the mainland for all these other intermediate groups and taking this type of approach to refine the colonization history of the island endemics. So an interesting thing to come out of this project was that the pattern of, or another interesting thing, was that the pattern of mitochondrial divergence suggested that the younger of the two islands. It's about 8 million years old. And that there was diversification in situ to form these two species of neutrons that are endemic to the island. And then that one of those species, the lowland species, dispersed from Sao Tome to Principe, which is much, much older. It's about 30 million years old. And that all of this happened within the past couple million years. So this is in contrast to a sort of rule in island biogeography that dispersal tends to occur from older islands to younger islands. This is really well known from the Hawaiian archipelago, for example. And so if this was, in fact, an exception to that rule, it would be pretty unusual. And I wanted to follow up on it with a sort of more robust data set, just because there are some limitations to inferring the evolutionary history of populations based on mitochondrial markers. And so this is a species tree analysis looking at a bunch of biallelic SNPs from a RADSEQ data set. And the reason that there are maybe not as many SNPs as some of you are used to seeing in these data sets is because of the divergence between the mainland sister taxon and the island endemics. It's harder to recover shared loci the further you step out. And you have to be biallelic and all of that. But anyway, the important thing is that this pattern of divergence is the same as the mitochondrial pattern of divergence, and again supports that we have dispersal to the younger of the two islands, that diversification occurred in situ, and that we have dispersal from the younger island to the older island in the archipelago. And so this exception to the progression rule, going from younger to older islands, indicates that there's some other characteristic of the islands that's generating this pattern of colonization and establishment within the island system. And for organisms like frogs that are going to be relying on some sort of assisted dispersal, it makes sense that another factor like maybe ocean currents would be more relevant to assisting your dispersal from one island to another, not necessarily island age. And there aren't many studies for organisms from these islands, let alone those that would be relying on vegetation rafts or assisted dispersal to get between islands. But the two studies that do exist, and these are mitochondrial studies, for skinks and geckos from this island system, these are also endemic species, are consistent with the same pattern of going from younger to older islands, and this is of course consistent with the currents in the Gulf that are going from south to north in this portion of the world. So again, it would be nice to get some information from some of the other species, but it does look like this island system is an exception to the progression rule, at least for these species that rely on assisted dispersal to move from one island to the next. So these analyses confirm that there was one dispersal event from the continent to the archipelago, and then that we had diversification within a single island, and then dispersal between islands in the archipelago, as opposed to multiple colonization events from the continent to the islands independently, because of all the island taxiform monophyletic groups. And so I wanted to look at divergence within a single island, and then also at dispersal between the two islands. So again, I'll remind you of the frogs. So we have the Sao Tome giant reed frog. Sorry, the frogs don't really like when you photograph their bellies, so these are all going to look like mug shots. But we have the Sao Tome giant reed frog, which is found at higher elevations. And currently, it's known from one tree. So you're only going to see one real sampling locality, and it's not because we haven't tried to find more, but it's a tree hole breeding species, so it breeds in large cavities that fill with rainwater. And they're just, as I'm sure you can imagine, kind of challenging to find. So we have one tree that has two cavities, and consistently when we check it, there are frogs in there, so that's great. But it would be nice to have a few more trees. Hopefully it will happen in the coming years. Anyway, so we have the Sao Tome giant reed frog. It's found at high elevation. It's pretty large for a reed frog, and it has this really nice orange and black coloration on its belly. And then we have the sister taxon, Hypoleus molleri, which is found from sea level up to 1,400 meters elevation. Here in his mugshot, you can see he doesn't have that coloration. And these guys breed in basically any available slow-moving or standing water. They're not picky. And as you move up to the higher elevations, to the elevations at which both species can occur, you find these individuals that have intermediate coloration, and they also have intermediate body size. And so this suggests some period or some extent of gene flow between these two divergent lineages, either throughout their evolutionary history or perhaps more recently following the period of secondary contact between once isolated lineages. And so this was just something that I saw in the field, but of course I wanted to confirm it with molecular data. So I collected samples along a kind of elevational transect, going from sea level and kind of meandering my way up to the top of the volcano. And I characterized all the individuals that I collected out of mitochondrial gene, and then also out of amyloid SNPs using the double-digest RASI protocol. And so I'll present the mitochondrial data first. So I recovered two very differentiated haplotype groups, this pink group and this yellow group, and they largely correspond to the mensis, the large species, and molari, the lowland smaller species. And I'm going to change these dots in a second. So the mensis individuals are always going to be squares, and then the molari individuals are going to be circles. And so you can see that the mensis individuals, and there's one that I caught at this site, always have this pink mitochondrial haplotype. And the molari individuals at low elevations have this yellow haplotype, but then at sites where the species are sympatric, we find individuals identified in the field as molari, or as some sort of intermediate, that carry this pink, primarily semensis mitochondrial haplotype. And my sample size for semensis is smaller, it's only 20 individuals, but I never found a semensis individual that had the molari haplotype, or the yellow haplotype. So I also recovered two differentiated genetic groups looking at this panel of SNPs, and this is just a structure analysis of K equals 2, which is the most highly supported number of genetic clusters. And these are organized according to elevation. So this is the highest elevation site, which happens to be a molari site, and then going down to sea level. And so these are the semensis individuals, which have really high assignment probabilities to this pink semensis scheme. And then these lower elevation individuals with molari show very little evidence of any introgression with that pink scheme. But then the sites where the species are sympatric have really high levels of apparent admixture. So again, this is consistent with the mitochondrial result of having some sort of gene flow between these two differentiated groups in a region of sympatry. And so you could have this pattern due perhaps to some sort of incomplete lineage sorting. If you had a period of divergence and the alleles just hadn't sorted out to form two different groups. But I think that the geographic pattern that we recover is a lot more consistent with the period of allopatry than secondary contact. So we would expect this incomplete lineage sorting, if that were the case, to be randomly distributed all the way throughout this species in all these different populations. But finding it concentrated in this region of secondary contact, or this region of sympatry, is a lot more consistent with it being secondary contact. And so to quantify the extent of this potential hybridization between the two species in just a slightly more rigorous way, I took a subset of the SNPs that were a little bit more stringent in terms of the minor allele frequency criteria that I used, and I ran them through this new hybrid assignment program. And this program assigns individuals with varying probabilities to either being parental genotypes, backcross genotypes, and then F1 and F2. And I didn't find any individuals that had assignment to the F1 category, so they're not shown in the legend. And so again, these are the sites colored according to elevation. And we have really high assignment to the parental genotype class and Microleus molari and semensis. And then again, at those same sites, we find a number of individuals that are being classified as F2, and most of them also as a backcross into this yellow parental type. And we do find a couple individuals that are assigned to the semensis backcross in the other direction. But it's possible that there's some sort of asymmetry in terms of the direction that the hybridization and backcrossing is occurring. And again, this is all happening at the same sites. So the question then becomes, if hybridization is so common at these sites where the species are sympatric, then how do they diverge to form these differentiated, phenotypically distinct, and genetically distinct groups in the first place. And I think one potential mechanism for this has to do with the availability of breeding sites on the island. So, as I mentioned, the larger species breeds in these large tree hole cavities. And at higher elevations on the island, here you can see that it's really, really steep topography. And you don't have very much standing water. In fact, the only standing water that I've ever seen is these tree hole cavities. There's no streams, there's no ponds. And in contrast, at lower elevations, there's slow-moving and standing water everywhere. And we find tons of breeding products of these types. And those types of breeding habitats are very common for reef frogs on the continent and also the sister taxons along the Ventris. And that's where this lowland species is breeding. So it's possible that this geographic separation of the availability of breeding sites and the types of breeding sites is what initially drove divergence between these two species. I still am trying to think about reasons that the large body species would decide to breed in tree hole cavities. That's a whole other question. But I think that that sort of allopathic distribution of breeding sites and the different breeding site choice of these species might explain some of this divergence in allopathy. And that this same mechanism could potentially explain what has brought these species back together in current times. And I'll just point out, this is Bob Drew, this is one of my collaborators, he got his PhD in this experiment just a few years ago. And he's a curator at the California Academy of Sciences and facilitated a lot of work on the island. So we're standing in the middle of the hybrid zone, and this is an agricultural field. And these are the sites that we find most of the hybrids in, and they're also sites that have these artificial breeding sites. So there's a lot of standing water and either tarps that people put in the fields, they collect water and they find frogs all over those, also cisterns. And so it's possible that agriculture moving up the slopes, abutting right up against the primary forest, and standing water that's associated with that agriculture has facilitated secondary contact between these species by increasing breeding sites in places where previously they were not connected. So there's very little standing water, so even at about 1,000 meters in these sites. And as a somewhat interesting coincidence, this is also the same sort of elevations and regions that the really well-studied Drosophila hybrid zone occurs at, so Drosophila saturnaria. And those species are ecologically differentiated in terms of the climates that they prefer, the habitats that they prefer. And again, the authors of those studies invoke this move of agriculture up the mountain slope and sort of this transition zone between secondary forest and primary forest as being a mechanism for moving those Drosophila species together. So we might have some kind of suture zone facilitated by agriculture in this region, affecting fruit flies and bugs. So finally, there's the hyperborean moai, which somehow figure out how to get from one island to the next. So I'll just talk very briefly about inter-island dispersal manipulation. So I collected samples from a number of sites on both islands, and again used a mitochondrial locus and the same axis data set. And basically, they're very differentiated in both data sets, so you don't find any shared mitochondrial haplotypes. And they form a completely distinct genetic cluster in the structure analysis. And so what this indicates is that although dispersal between the islands was possible at some point in time for reef frogs, not ongoing, so it's not a very common occurrence. And I should say also that none of the other amphibians have successfully dispersed from one island to the next. So it doesn't seem to be a very easy thing for amphibians to do when that has happened. And what's kind of surprising about this again is that it happened relatively recently in terms of the evolutionary history of these islands. So this dispersal event happened sometime in the last million years, we estimate. And in Principe's 30 million year history, again, that's pretty recent. And so, and I'll just mention, so there are two other endemic species that and then the Principe petal frog is a very small leaf litter species. So they're ecologically pretty different from reed frogs. And so another sort of rule in island biogeography is that it becomes more difficult for new species to successfully establish themselves on older islands because a lot of the niches have been filled already. But in this case, at least in terms of the amphibians that are present, there could of course be organisms that are not amphibians that would have a lot of overlap with reed frogs. But in terms of the amphibians, it doesn't appear that there would have been much competition for the sort of role that reed frogs play in the ecosystem. So what I think is really exciting about this group is that they showed us these really unexpected patterns in terms of these broad-scale rules that we kind of think of in island biogeography. And so even though we think of in situ diversification as becoming more dominant as islands are older, there's kind of this weird pattern for organisms that rely on this assisted dispersal to get to islands, which are kind of these sweepstakes events that don't happen very often. Over a long period of time, those are still occurring. And so you still have this important role of dispersal in generating endemic species, but in groups that we tend to think of as not being very good dispersers. So it's kind of this weird interaction. But I think that's a pretty exciting outcome of this project. And so just to wrap up this part of the talk, we found that there are at least 2 possible colonization routes from mainland Africa, one of which hadn't really been identified before as a potential river system that would serve as a source for these vegetation rafts colonizing the islands. We found that there's likely a period of allopatric divergence that drove the in situ diversification on South Tome Island, but that now there's secondary contact between these lineages, and maybe that's been facilitated by agriculture, expanding the range of one species up the mountain. And then we also find that although dispersal is possible for reed frogs between islands in the archipelago, that it certainly doesn't happen very often, and that these populations are now on independent evolutionary trajectories. And currently, we haven't found any phenotypic differences between these populations, even though they're not exchanging genes. But we haven't looked very closely, so we'll be doing that. And maybe there will be a Hypolius drusei in our future. Okay, so now I'm going to shift gears and talk a bit about the work that I'll be doing at the NPC. And it's focusing on the evolution of sexual dichromatism in reed frogs. So sexual dichromatism is just sexual dimorphism in color, so species in which males and females are different colors. And I make a distinction between 2 primary classes of dichromatism because they differ in their phylogenetic distribution across frogs, but I think also they differ in terms of the underlying genetic basis of the trait and then also the function of the trait, so the ecological function. So the first class, which I won't be talking about today, is dynamic dichromatism. And then this is just a case where there's a temporary color change, and it seems to happen predominantly in males, and it coincides with the breeding season. And so this is not a painted frog. This is actually the color the frog is. And this is a European species, and males turn bright blue for several weeks during the breeding season, and then afterwards they go back to being normal colored. So there are a lot of interesting studies on the function of that bright blue coloration. And then the other class is ontogenetic dichromatism, and this is where males or females undergo a permanent color change, and it looks like it always coincides with the onset of sexual maturity. And so this is a reed frog species, and maybe we'll take a vote. So who thinks that this is the male? Okay, so who thinks that this is the female? Oh, sorry. Maybe this is the male. Okay, yeah, so this is the female, and this is the male. And yeah, this is Hypolius argus. So, and the juveniles look like this.
That's a juvenile.
That was the male, but the juveniles would look like that as well. Yeah, so the female undergoes the ontogenetic color change and turns crazy.
Are they breeding these at Calicut?
They're trying.
Yeah, okay.
But not that specific species.
Okay,
Yeah. So, ontogenetic dichromatism is common in, well, it happens in frogs in a whole bunch of different families. but it's not super common. But it's actually quite common in the African recon filling, the hyperoliety, which I'll zoom in on. So this is a not good phylogeny of the group. But even at this level, so there are over 200 species in the family, and this is just a subset of those species, like a mitochondrial tree. And here I just colored the sexually dichromatic species in orange. And so even at this scale, you can see that there appear to be multiple gains and losses of the trait throughout the family. And in some of these species, the male is kind of cryptically colored, and the female is more conspicuous. And then we also have species where males and females are different colors, but one isn't necessarily more conspicuously or cryptically colored than the other. And I'm working with a graduate student in the laboratory lab at UC Berkeley, Dan Kordick, to resolve a much more robust phylogeny of the group, and we're hoping that with that we'll be able to answer more questions about how many times this trait has evolved across the family and what is the sort of large-scale ecological correlates of larvae dichromatic, and get at it from sort of a more macro perspective. But what I'll be talking about today is the other side of that, trying to look at it from a individual species perspective. So first, I'll give a little background on what we do know about dichromatism in reed frogs, which is not that much. But so a lot of the species have these distinct juvenile and adult color phases. And from what we know about the few species that have been looked at, this appears to be driven by the onset of sex steroid hormones being released at the onset of maturation. And so in some species, both males and females change color. And so even though there's been this ontogenetic color change, the resulting species is still sexually monochromatic. But then if the color change pathway is disrupted in just one sex, so in this case the male, then you end up with a sexually dichromatic species as their adult. And so that sort of, if it is this simple, that might explain why we see multiple shifts throughout the family and what appears to be relatively high evolutionary ability of this trait. But again, we still don't know a lot more than we think we know. So, how about this one? Do you guys want to do another quiz? I'll try to do a better job of asking the question. This one is the male.
Practice matter?
Yeah, you guys know this one. It's more famous.
No.
Okay, fine.
Eclectus.
Yeah, this is the eclectus parrot, and so this is the male, and this is the female. And these sorts of systems, which have been much better studied, can give us a little bit of insight into maybe some of the mechanisms that might underlie having what appears to be bright coloration in females. And so potentially these sexual color differences could serve in species recognition and mutual mate choice. Males and females could also be spending time in different habitats and different light environments, so that a coloration that appears to be really conspicuous to us, but in other contexts is actually cryptic in the light environment. And so that's sort of where I'm drawing some of my thoughts for things that could be happening in reed frogs that are feeling much less about the ecology of these species. And none of these types of hypotheses have been studied in any frogs, let alone reed frogs. But there has been some indication that male frogs, because they're the ones that are making noise at breeding, because they're calling to attract females, might be more susceptible to predation at those sites, and that maybe having a more cryptic coloration at those sites would be beneficial to avoid predation. But it doesn't really explain why the female would go to the trouble of changing color when she becomes sexually mature. So even if that does end up being an important part of the story, I don't think it will be the only part of the story. So to try to understand the evolution of this trait and also the function of this trait, I'm focusing on a species that's found on Bioko Island, Equolis tuberculatus. And the species is distributed throughout Central Africa. And we don't know much about its breeding biology, but it seems to breed in sort of edge habitats, and it seems to have normal sort of reed frog, parental care, and eggs only in the water, but there's no nest guarding or anything like that. Males call to attract the males. We don't really have many observations of what happens when the males and females encounter each other in terms of if there's And the reason that I've chosen to focus on this particular species is that it has population level variation in dichromatism. So I found a population on Bioko Island where some of the males assume the female coloration, but a very small portion of them, and most of them have the normal sort of juvenile coloration. They keep that even when they become sexually mature. And the other reason that I've chosen to work on this population is because it's on Bioko, there are no large mammal predators around, and so you don't have to worry about getting trampled by elephants when you're trying to observe frog behavior. Okay, I'm sorry, here's what they look like. So this is what males look like, and this is what females look like, and then there's a small proportion of males in this population that also have this female coloration. And so I'm just going to give a quick aside about why I was even on Bioko Island in the first place, in case that popped across your mind. So Bioko is the fourth island in the same archipelago that I was talking about earlier, but it differs from the other islands in that it's a land bridge island. And so it's only separated from the continent by a very shallow sea, and that sea level has retreated and then risen repeatedly in response to global glacial cycles, which means that there have been periods of isolation and connectivity between organisms on the island and the rest of the continent. And potentially these periods of isolation and connectivity, especially for organisms like frogs that aren't going to disperse across saltwater, most likely, then that provides an opportunity for genetic differences to build up. But then when the sea levels retreat and the populations come back into contact, either for those genetic differences to become erased, or if it's been long enough that they've built up some other sort of commuting barriers for those species, for those populations to become distinct species given enough time. And so I thought it was a nice sort of contrast to these volcanic oceanic islands that I've been looking at in the archipelago. So here's my little cartoon of maybe what happens. And there are two reed frog species that occur on the island. So that was how I initially had started working there. And just to give you a sort of brief overview of the diversity on the island, so again, there hasn't been very much work done there, but because it was connected to the continent, the flora and fauna are much, much more diverse than Sao Tome and Principe and Levant, the volcanic islands. But most of that diversity is shared with adjacent Cameroon and other parts of continental Africa. So really, really high numbers of species, but a very small subset of that is endemic. And so, for example, we have 52 species of amphibians, but only 2 of them so far have been described as being only found on Bioko. And that's true across most taxonomic groups. And what that kind of suggests, and again, there hasn't been much work done on this yet, is that if there are genetic differences that are accumulating during periods of isolation when sea levels are higher, in most cases, it looks like that is being erased by subsequent gene flow when those populations are coming back into contact with the continent. But maybe we have to look more closely, and maybe some of these species are impacting on it. So for the 2 reed frogs, in case you were curious, we would expect that at least we would find divergence that dates to about 10,000 years, or 12,000 years, which is the most recent sea level incursions. And what we find is actually much older divergence than that, and it differs between the 2 reed frogs that we looked at. So we have Hyporleus tuberculatus, which is the one that has the variation in dichromatism, and that divergence is on the order of tens of thousands to hundreds of thousands of years. And then we have Hyporleus oscillatus, which I haven't told you about yet, but this is another sexually dichromatic species that's also found throughout Central Africa. And that divergence between Bioko and the continent appears to be much older. And so this could indicate that differences in the habitats that these species use are maybe affecting whether or not they're able to disperse across the land bridge, even when it's exposed. The types of habitats that are present might not be conducive to dispersal and gene flow in Hyporleus oscillatus, even if they are for tuberculosis. But it certainly is more complicated than just a single riparian event when the land bridge is formed. It looks like there's a lot more going on. And whether or not this divergence is to Hyperoleus tuberculatus. Again, we have a subset of males in this population that assume the female coloration, which is nice because it means that we can try to look at the genetic basis of this trait without worrying about the influence of demography and shaping genetic differentiation. This is a single, from neutral markers indistinguishably, just a very mixed population. So hopefully we're able to at least eliminate differences in demography when we're comparing these males from the other males in the population. And so the plan, what I've been working on now, is looking at gene expression data using RNA-seq from skin and liver tissues in normal colored males, females, and then the female colored males, and also trying to link that to the pigment composition in the skin. So it looks like a lot of these color differences could be driven by carotenoids based on what we know about frog coloration. And so we're trying to link the composition and abundance of carotenoids in the skin with differences in gene expression. And then also trying to do some hormone-induced color change experiments. So this is one of my first results, and this picture is not great. But this is a male that I exposed to estradiol for a week, or for a month, sorry. And yeah, I really can't see. But anyway, he did start changing color. So it looks like I can do this hormone-induced color change, and then again look at differences in gene expression between control males and males that have been exposed to estradiol. And then complementing that with some ecological work in the field. So trying to get a handle on where these frogs are going during the day and at night, what types of substrates are they selecting, are they cryptic on those different substrates, and does that differ between males and females? And then trying to look at that from the visual perspective of potential predators, which we don't really know who they are, but we can use sort of generalized avian and mammalian vision models for that. And then also whether or not the frogs know their different colors and can they see these color differences in low light conditions. And so I did horrible things to frogs and dissected out their retinas and tried to quantify their visual system. And so looking at the different pigments that they have and what wavelengths they can absorb. And they do have two different types of bronze, which is not uncommon for amphibians that are operating in low light conditions. And so there's the potential that they can see these differences in certainly brightness, but maybe even color between males and females in low light conditions. So with that, we can move forward and maybe think a bit about whether or not there's the potential for mutual mate choice or species recognition in this system as well, as a complement to this maybe more natural selection, avoiding predation function, which I'm not fully satisfied with as the sole explanation. So with that, I would just like to thank all the people that have helped me in the field and people that have provided funding and just logistical support. And I'll leave you with a short poem that someone wrote in response to a National Geographic blog that I wrote about some of the work we were doing on the islands. And I just found that it very nicely captured what I was trying to do, but then also kind of made fun of me. So.
Rayna, thanks for the great talk. Back on the hybridization with the giant refrog, I'm wondering if there's any mate choice data to suggest that maybe small males like big girls in terms of asymmetrical mitochondrial pattern.
Yeah, so that's one of the other possibilities, and we also don't know anything about differences in viability between different classes. But my thoughts, and this is very hand-wavy, is that the males are just going to go to their breeding site that they identify as being suitable, and they're going to start calling. And females are going to hear males calling and go to that site. And in the case of a big girl, of a large species female, the smaller males are at elevation that she's hanging out in. And so she hears males calling, and their calls are very similar. They might be slightly different because the larger species is larger and that can influence So she just hears males calling, and so she goes to that breeding site, and it happens to be a site that's full of small species males, but she's like, okay, whatever, I'm here. The large species males go to these tree hole cavities that are pretty sparse in the forest and probably kind of hard to find, and also not at sites that the small species males are likely to be hanging out in. And so I think it's less likely that they'll encounter each other based on those differences, maybe in just the breeding behavior of males and females.
So
I have
not
found,
necessarily choice.
well, I'm not sure. I did find, so the one individual that I found, not a special tree, as we call it, was a female, and she was in amplexus with a small species male in a cistern. So I was like, yes. Like, this is the best observation I could have. But it's another one. Yeah.
So Yoko is what, about 12,000 years separated, I guess.
In the most recent.
And your frogs, your reed frogs, there are beautiful. So, but I'm just wondering for some of the other amphibians there. I mean, is there? You would think that there would also be contemporary gene flow. You've got the Nyong River, you've got the Sanaga River that are about 60 kilometers away. That are big rivers. Any evidence for that?
Most of them haven't been looked at all from an molecular perspective. So, yeah, so the answer is there's no evidence, but it certainly doesn't mean that it's possible.
But you sampled, your reed frogs, you did sample in Cameroon as well, so you know that the Principe and Sao Tome frogs could have been coming from, say, one of those rivers.
Correct, and Cinnamomia ventris doesn't occur that far. It just barely gets into Cameroon.
One thing you might look at is some of the banana quid data, which suggests that island populations actually were the ones that colonized the mainland. I don't know if you're aware of those papers.
Yeah. So I think for Bioko that can end up being true, and ironically for one of the species, the translocality is actually Bioko, so it would be really cool if it turned out that that was also the source. But I do find some evidence, and for that data set, it's not a NextGen data set, but I do find some evidence that looks like there was some reciprocal migration from Bioko back to the continent, sort of both in Cameroon in the reef frogs.
In terms of the variation within the species of how and what sex are dichromatic, etc., is there a variation or like supposed variation in which gender or sex is more susceptible to sexual, or is the one that's more picky about its sexual partner? Is that equidistant between these species, or like are males, or is there a variation between which male and female is more selective with its mate?
That's a good question. Yeah, we don't know, we just don't know enough about the breeding biology of any of these species to say that for sure. But it would be worth trying to figure out, yeah, is there any sort of correlation with choosiness and whether or not there's even a preference for these different color morphs. So that was why I tried to figure out if they could even see the difference in coloration. Like, do they know if they're looking at a green frog versus an orange frog? Would be the first step.
So, as you said, a lot of species are ontogenetically changed colors.
Mm-hmm.
And then some of them, if that model is correct, one sex or the other males on the new color. So that ought to mean that in principle, at a phylogenetic level, that the dichromatic species are phylogenetically nested within clades that change color ontogenetically that are monochromatic. True or false?
That's what I mean in the phylogeny.
We've got a phylogeny.
I would not trust anything that that phylogeny says. Other than that they're
You trust some of it. I mean,
well,
you're willing to say cinnamon ventris is.
oh, that's a very different. So that phylogeny I showed was just a mitochondrial, the one that had like orange lines on it. Yeah, that. Also, that just doesn't include enough of the diversity in the family to say for sure. But yeah, so that phylogeny is like 30-something species out of 200, and it's based on 60 nests. So yeah, so I wouldn't really trust that robustly. But I'm disagree with you that would make sense. And speaking of Cinnamomea ventris, which is now clearly a species complex, even beyond just the island endemic species being nested within it, that species on the continent is primarily sexually dichromatic. There was a new species recently described that's nested within it, and those authors didn't fix the taxonomy of the group. But anyway, that species is monochromatic. So neither sex undergoes a color change, actually. They both retain the juvenile coloration. And then the endemic reed frogs are sexually monochromatic. And I found...
oxygenically change or not?
It appears that yes. So I found a almost metamorph individual, and it had a different coloration than the adults do. So I haven't found juveniles, so I don't know for sure what juveniles look like, but this metamorph had a different coloration than the adults do.
That's in the giant one.
And it was the low elevation one, but neither one is dichromatic. So they both apparently are undergoing a color shift, but are monochromatic.
Yeah.
And they evolved from a dichromatic ancestor, presumably.
Presumably.
Yeah.
How much also is known just, across that diversity of different species, whether it's probably well known whether the adults are dichromatic or monochromatic, but
Yeah, it's fairly well known. Yeah, we do
what
have.
about oxygenically? I mean, are there juveniles that you can assign to the species so you can
No,
ask
I mean,
whether or not there's an oxygenic change?
Part of the problem for most of this diversity is that it's largely undescribed. So most of these widespread species are turning out to be 4, 5, 6 distinct taxa, and you find them sympatrically, and you thought they were the same frog, but they're actually completely different. And so I think we need to get that all sorted out first. And then there's also a lot of morphological or phenotypic variation, especially in color within species, and not necessarily very much between species. So you can have greater variation in coloration that's not even necessarily dichromatic within a single species than you do between completely distinct species.
Assuming one of the exceptions, right? I mean,
But even in ones that I've confirmed that these are the same with molecular data, and they look very, very different. And then likewise, when they're like, oh, I wasn't even sure if this for sure is a Cinnamomea ventris, and it turned out that it is. So yeah, it's a very, very messy group, but I think they're pretty exciting.
Are you familiar with Amier's work?
Yeah, so
Is he
Cameroon
pretty good at distinguishing these species without molecular techniques, or is he way off?
It depends. He has the best handle, I would say, on what's going on, but in Cameroon.
Yeah.
And that's part of the problem, I think, with this group historically, is that people have worked in one country, or maybe 2 countries that are next to each other. And these species ranges, of course, extend far beyond those. And so Amier's oscillatus could be completely different from someone else's oscillatus who works in Gabon, or, so that's been really challenging. But he describes, for the reed frogs that I'm looking at, these 3 different morphotypes in Cameroon, and it looks like that's holding up with the patterns of divergence that I'm finding. So he might be right about some things, but those are based on, he says, like the dots, the polka dots are bigger in this species than in this one.
Yeah, I don't think you ever picked up a 5 feathers, but.
No, but well, for some of these, maybe you don't need to.
and one more. Yeah. Peter.
Thank you very much for the great talk. Rayna, it seems like your system is just begging for call analysis. I was going to ask you, for example, on South Tome, when you have the lowland species coming out or overlapping with the highland species, do you find any evidence of character displacement in calls in that form?
I don't, but that's one of the next things that I want to do. Yeah, and so I tried to record the big species males calling, and there's some sort of really, really loud orthopteron that just messed up all my call data. And so I just need to do a better job of using the directional microphone to not pick that up. But you can hear the frog calling in the recording, but when you look at the images of the spectrogram, there's just this big black smear.
Bring Peter with you.
Yeah, yeah. Do you want to come to South Tome?
Okay. All right,
Yeah.
and as we visualize Peter going to South Africa,